So this is a joint work with Vincent Fröse and Volk Niedermeyer. And so let's consider this following scenario. We are a streaming platform and we want to filter speech in real time without actually having to do speech recognition. So we have this signal, and for the rest of the talk, we will use the word time series and string interchangeably. So don't worry about that. And let's assume we already have a tool that can split this speech signal into separate words. And now we want to take each of those words and compare it with a set of words in a database. For example, with bad words to bleep them out. So in this example, we might not see a similarity between those two words, but in a different example, we might see some similarity. And now the question, of course, is how can we actually measure the distance between the two time series? So how can we decide if they are the same word or not? And for this, we might want to try to use the Euclidean distance, but then we run into several problems. Those time series could have different input length, and the Euclidean distance only works for the same length. They also could have different time resolution, and then we would have to stretch out, for example, some of the time series. And they could also have local stretches when certain vocals and certain words are stressed more. For example, this peak in the two time series could be the same vocal where it is more stretched here in this lower time series. And to solve all those problems, Sakue and Chiba came up with this dynamic time warping distance. And here, the main idea is that we can copy any data point of any of the time series arbitrarily often. So what would this look like? Here we have on the left side the original two signals, and on the right side we have the warped signals. And here you can immediately see that, for example, those peaks we talked about earlier here are now aligned. And also, for example, the first red peak here is way later in the original series, and now when after warping, they are also aligned. And the computational task for this problem is to then obviously find this warped version that minimizes the Euclidean distance. And this can be done in quadratic time with a simple dynamic algorithm. And in practice, this is done almost linearly when we allow some error. And also this quadratic time has been shown to be asymptotically optimal in several papers. For example, by Bringman and I, who talked about this shortly yesterday. And some related problems are, for example, closest string, and especially when we talk about those conditional lower bounds, also the edit distance and longest common subsequence are mentioned together with the dynamic time warping. So now that we can compute distances between those signals, one might wonder how we actually got the signals in the database. And we could get them by, for example, averaging many recordings of the same word. But in this regard, it's actually not clear what averaging means. So here, to illustrate this, we have two sine waves that are phase shifted. And if we now would just compute the Euclidean average, we would end up with this red meaningless line. But what we would want is maybe something like this, which represents the sine wave shape. And to get something like this, we would have to compute the mean in the dynamic time warping domain. So this means we would have to find the mean that minimizes the distance in the dynamic time warping domain. So it minimizes the dynamic time warping distance to each input stream. But computing such a mean is very hard. And recently it got proven that this is actually NP hard. And the best known algorithm is n to the 2k something is also proven to be asymptotically optimal. So instead of focusing on this very hard problem today, we focus on an easier version, namely the binary dynamic time-hopping mean. And here we restrict our input signals and our output signals to be only binary. So we have k binary strings of length at most n, and we want to find a string z that minimizes the dynamic time-hopping distance to each of the input strings. And about this problem, we already know that this is polynomial time solvable in k times n to the 3. And for the binary dynamic time-hopping distance, we also know that this is actually solvable in subquadratic time in n to the 1.87. And now in our paper, we show that for the binary dynamic time-hopping mean, we can improve. We can actually compute it in k times n to the 1.87. And you might notice that this exponent is very similar to the one from About et al. And of course, this is not a coincidence. And we will see why this is on the next few slides. And our other algorithm works with basically run length encoded time series. And here m is the maximum run length encoded length, and mu is the median run length encoded length. And we also show some linear time algorithms for small k. So now let's look at an example for this binary dynamic time-hopping mean. Here we have 3 input strings, and note that they all end and start with zeros. And this has a reason, because today we just look at the easier version where all strings start and end with zeros, which saves some technical difficulties in the proof. And for those 3 input strings, I claim that this z is a mean. So let's look at the distance between each of the input strings and the z. For the alignment of z and s1, we can warp this 0 and this 1, and then everything is aligned perfectly. So our distance is 0. For z and s2, we have to make some mistake, and we will see in a moment why. So we have to, for example, align this 1 with the 0, and then we get the distance of 1. And for z and s3, we can again align the 1 and the 0 here perfectly. So we get the distance of 0. And so the total cost of this mean would be 1. And now we need to define some concepts to talk about this more efficiently. So first of all, we need to define blocks, which are just the maximal substrings of the same symbol. So we have 5 blocks in the first and third string, 0, 1, 0, 1, 0 blocks. And in the second string, we have only 3 blocks. And this is also why we had to make a mistake, because in the mean we have 5 blocks, and in S2 we have only 3 blocks. So we have to align some block multiple times in S2. And a condensation of a string is just if we take all the blocks and reduce them to length 1. And you can see that Z is, for example, a condensation of S1 and S3. So at this point, we can already make some observations. First of all, we can see that Z should be condensed, because when we warp later on, we can copy all symbols and all the blocks arbitrarily often. So we can make the blocks arbitrary length. And if we start with length 1, then we never make a mistake in the wrong direction, basically. And also, you can see that Z should not have too many blocks. For example, if Z has more blocks than this, imagine there was an additional 1 and additional 0 here, then we could already align this part perfectly to everything in S1 and S3, and then we just have garbage at the end, which gives us a higher distance. And at this point, if we know that these should be condensed and not have too many blocks, we can already see that there's only a small number of means that we have to consider. And now all that's left to do is compute the distance from each of those means to each of the input strings. And to do this more efficiently, we need the intermediate problem from which we can basically reduce to our problem. So here we have a small framework of the problems. And on the top here, we have our binary dynamic time looping mean. And right next to it, we have just the binary dynamic time looping distance. And below, we have this problem MSS. And this is called min-1 separated sums. And here we have m integers, and we need to choose r of them such that they are 1 separated and minimal. And 1 separated just means that we cannot choose 2 neighboring integers in the sequence. So for this problem, about it, I showed that if we can compute it for 1r, then we can also compute the binary dynamic time looping distance. And in their proof, they actually computed for all r using this complicated problem at the bottom. And now we use actually either their solution to solve this problem for all r, or we use our own solver for that. And if we have all the solutions, then we can use them to compute the mean. And in the next slide, you will see how we do this, how we get from min-1 separated sums to binary dynamic time looping mean. But we will not focus on how we compute the min-1 separated sum solution. So here we have an example for this min-1 separated sums problem. We have the sequence of integers. And remember, we have to choose r of them that are 1 separated and minimized. So for I equals 1, we can just choose the 1. For I equals 2, we can choose the other one. And now for I equals 3, here we could only choose this 5 or this 4. Or we can drop the 1 and instead choose the 2 2s, which is better. And for I equals 4, we have no other choice than to choose every second integer. And now the magic happens. So assume the sequence of integers is instead a sequence of block lengths of a binary string. So we have 4, 2, 1, 2, 5, 3, 1, exactly the same block length as the sequence of integers. And then also we have those additional zeros at the start and at the end. And now we want to compute the distance between this string and some mean candidates, which are condensed. So we start off with the condensation of the string S. And for this, we already know that we can align it perfectly. And so every 0 and every 1 is aligned. And we get the cost of 0 for this. And now if we make it shorter, then we have to make some error. So we have to align some block in the string S wrong. And of course, we choose the smallest block. So we align this 1, misalign this 1. Now, if we make the string even shorter, we have to make another error. And we can choose the other one. And now, if we make the string even shorter, then we have to make one more error. And we can see that the optimal solution is also taking those 2 2s And now, why couldn't we choose the 1 actually? Why can we not choose this 2 to make an arrow and this 1 to make an arrow? So to do this, we would have to align this 1 block here to this 0 block. And then we would have to align this 0 block here to this 1 block. But you can see that then we have no blocks left to align this block of size pi. So if we would try to make arrows 2 times in a row, we actually just waste 1 block. So just for completeness, if we have only the 0, we have to make arrows on every second block. So we get exactly the same pattern as in the min-1 separated sums problem. And now the proof to our algorithm basically works like this. We first restrict the number of mean candidates as you saw before. So we know that the mean should be condensed and the mean should not have more blocks than the run-length encoding, which just means more blocks than any strings has blocks, basically. And then we can restrict our number of candidates to n. And in general, if we also allow to have starting ones, then we have 2n. And now all that's left to do is to compute those distances between candidates and the inputs. And for the shorter ones, we saw that we can do this by computing the min-1 separated sums problem. And for longer ones, it's actually easy to see that you only have to count how many garbage blocks you have in the mean. So that can be done in constant time. So in the end, we end up with this time. For each input string, we have, for the longer blocks, maximal time n. And for the shorter means, we have maximal the time that's needed to solve this min-1 separated sums problem. And now all that's left to do is to sum up the distances and choose the best one. And here we can see some comparison of the slightly improved k to the k times n to the 2 algorithm. This basically just uses a basic dynamic program, but with some tricks. And our program that runs in this run length encoding time, dependent time. And here we can see that we have data with sparsity 0.1. And sparsity here also means what is the ratio between the run length encoded strings and the non-encoded strings. And we can see that we can already get speedups up to factor 100 here. And for even sparser data, we can get speedups of almost 1000 here. So to conclude, what we did is we showed that if we have this linear time at the start to encode the strings and at the end to sum up the distances, then we only need to solve min-1 separated sums to get this solution for binary dynamic time warping mean. And in our paper, we also showed that for small k, we can actually solve this in linear time. And for larger k, we conjecture that it's not solvable in linear time, no matter how much time we can allow in terms of k. So we think that you always have to solve this min-1 separated sums problem in some form. Thanks for your attention, and I'm open for questions.
Okay. Thank you. Are there any questions?
Well, I have a short one.
Yes, please.
So, my question is, if you make